All right. Hi, folks. This is our second lecture. Sorry it can't be live. Um, so let me go back to one of the operations, a couple of operations we looked at on Tuesday. So the union and the intersection. Recall that the union of two sets is the set which consists of all elements which are either in one set, let's say A, or the other B. And we have the notation that you see on the slide. For the intersection, similar notation, except rather than having a U, it's upside down. The intersection of two sets A and B, this is the set consisting of all elements which are in both A and B, right? And so now let me go a little further down to generalized unions. So what we want to do here is basically define the union of several sets. Now, you can either invoke the associative law that we saw very briefly for the union, but if you think about it, if you take a whole bunch of sets, it's natural to define the union of these sets as all the elements which are in at least one of the given sets. And we have a notation which you can read. It's similar to the sigma notation. So if I have sets A1 to AN, then the union of these sets is denoted as union I equals 1 to n of the AI, which is what you expect it to be. It's the set of all x which belong to at least one of the sets A1 to AN. You can, if you have in a sequence, an infinite sequence of sets, you can also write it with that notation, very convenient. We won't deal with that very much, but there you go. Might as well extend it while we're at it. There are a couple of exercises, I think, that deal with infinite unions of sets. So it's exactly what you think it is. For intersection, you just take this slide and you flip all the unions to intersections, right? So the intersection of n sets, A1 to AN, what is that? This is the set of all elements which belong to each one of the sets A1 to AN. And we have the notation similar in flavor to the sigma notation, which you see right there. And if you have an infinite sequence of sets, A1, A2, right up to whatever, no one, you have an AI or AN for each positive integer, and then the intersection is as you see. So it's the set of all x that belong to all of these sets. Okay. Here's another little topic which is interesting. Especially if you think in terms of how data is represented in a computer. So if we're handling sets in a computer, one way to deal with them is using bit strings. And so I'm going to show you the basic way of doing this, and then we'll see how this has an advantage when you're doing operations on sets. Okay, so let's suppose that we have a universal set U, and I will assume that it is finite. So think again, we're working inside a computer. We have a finite set U, or universal set, and I'll name its elements A1, A2, right up to AM. And what I'd like to do is to use bit strings to describe its subsets, right? So again, I remind you, if you have a universal set, all of the sets we're interested in are subsets of this set. So let's say I have a subset A of U. So it contains some, or maybe none at all, but some of the AI. So what I do is I create a bit string. What's a bit string? It's a sequence of bits. What are bits? Zeros and ones, right? So the word bit comes from binary digit. So a bit string is just a sequence of zeros and ones, okay? So if my universal set has n elements, A1 to AN, the bit strings I'm interested in have length n. So you have a sequence of n zeros and ones. And given a particular subset of U, call it A, then I'm going to associate to it the following bit string. You put a 1 in the ith position if AI is an element of big A, and you put a 0 otherwise, okay? So this is the formal definition. If that doesn't really mean anything to you right this second, I'm just going to give you some examples and you'll see exactly what this is about. It's very simple, okay? So here is our universal set in our example. It's all positive integers from 1 to 10. And I'll think of A1 as 1, A2 as 2, and so on, okay? And now consider the set A consisting of elements 1, 3, 5, 6, 9. So what is its associated bit string? So it's a bit string of length 10, right? And you put a 1 in the place where AI belongs to, in the ith place if AI belongs to big A. So here I have a 1 in the first position because 1 is there. I have a 0 in the second position because 2 is not there. And then I have a 1 in the third position because 3 is there, and so on. Okay. Now, if you're wondering why there are spaces here, is just for readability. If I give you like a really long sequence of bits and there are no spaces, it's much harder to read. So it's fairly standard to do something like that to be able to read it more easily. So we have spaces at every 4 bits starting on, let's say, on the right. Okay, so here basically the ones are in positions 1, 3, 5, 6, and 9. So this bit string, it encodes this subset of our universal set. Okay, and if you think about it, if you take any bit string of length 10, there is some unique subset of U that corresponds to this bit string. So for example, if you take the bit string all zeros, then that corresponds to the empty set, right? And if you take the bit string, sorry, all ones, then this will correspond to the set U itself, the whole universal set. Now, so these are, if you look up the exercise, you'll see that you'll be asked to interpret the basic operations on sets in terms of bit strings, but just to show you one of them, okay? So if this, let's say we have a set A which has the following associated bit string 10 10 11 0010, what is the bit string of its complement? Well, that's clear, right? You just, whatever element was there, it's not going to be in the complement. So if you had a 1, it'll become a 0. And if it's a 0, it's a missing element in A, then this element must be in the complement, so it becomes a 1. So basically, if you have a bit string for a subset, what is the bit string for the complement is you just flip all the bits, right? So it's a very simple operation to perform on bits, right? If you think about unions and intersections, you'll see that there are corresponding very nice ways of interpreting this on bit strings, but I'll leave that for the exercises. I'll leave you play with that by yourselves, okay? Another interesting consequence of this this correspondence between bit strings and subsets is we can actually count the subsets of a set in a very simple way. Now, I'll get back to this, but let me just try to do this here. And if you get it, that's fantastic. If you don't quite get it, try to get it. And if you really don't get it, don't worry. We'll get back to this in chapter 6, I think, when we're going to talk about some basic combinatorics. So we'll get back to that. But while we're here, let's think about this following problem. I have a universal set that has n elements, and I'd like to count the number of subsets of this universal set, okay? Now, we've just argued that this is the same thing as counting the number of bit strings of length n, right? So for each subset of U, there is a bit string of length n, and there's exactly one. So there's the same number of subsets of the universal set as there are bit strings of length n. So let's count those, okay? How many sequences of zeros and ones of length n can I write down? Well, here, hopefully this argument will convince you. I have a choice of two possibilities for each position. So for the first position, I have either a 0 or 1. For the second position, I have either a 0 or 1, and so on. And I have n bits. So that's 2 times 2 times 2, n times. So that's 2 to the power n. Okay. If this doesn't convince you, and it's quite fine if it doesn't, okay, here's another way of thinking about it. Let's write numbers in binary. Okay, so so it's a completely different way of seeing the following the argument I just gave you. So the numbers that I can write down in binary on n bits, these are so I can start at 0 and then I can go to 1 and 2 and 3. The biggest one that I can write is all ones in binary, and that happens to be 2 power n minus 1. So 8, that's a total of how many numbers from 0 right up to n minus 1. That's 2 power n different numbers. Okay. Again, if that doesn't convince you, if you don't like that, we'll see binary shortly. And so I can clear that up. Okay. But in any case, the resulting statement is that if you have a set of n elements, then it has 2 power n subsets. Hence the name power set, right? That's why this set of subsets that we talked about last time is called the power set. Okay. Let's move on to section 2.3, functions. Yeah, before I do this, well, okay, let me just introduce this section, and then I'll go back to relations for just a little while. So what I'm going to do here is theoretically review, but I'm not supposing at all that it's review. Okay, I'm going to suppose you've never seen this before, but you're just smart people and you can follow what I'm talking about. Okay, functions, the functions that you've seen, most of them in your life were functions from the real numbers to the real numbers, most of them. You've seen other functions, but you didn't see them as functions, like sequences. You might remember sequences from Cal 2. These were also functions, but from the natural numbers, the real numbers, but they weren't introduced that way, and it's not necessary to think of them that way. But the functions are a very, very flexible, universal concept. And in our context, we're going to see them, we're not going to see functions of a real variable like you saw in calculus. They're very different. But in any case, in computer science, where are functions used? Everywhere, but in particular, if you are considering complexity of algorithms, then you'll be looking at functions which compute the time or space that an algorithm uses in terms of the size of the input. In cryptography, one-way functions, and we will see that in chapter 4, for public key cryptography, this is absolutely fundamental. For cryptography also, permutations, which we will see in just a few minutes, are important. And of course, well, they're all over the place. Okay. So let's go back to relations just very briefly, right? Because we're going to see functions as special kinds of relations. Sorry for flashing this stuff. Here we go. Okay. So we've defined a relation from a set A to a set B as a subset of the product A times B. So it's a bunch of pairs where the first entry is from the set A and the second entry is from the set B. So that's what a relation is. Okay, it's a very flexible, very general definition. Now, functions are relations, but a special kind of relation. So let's go back to functions. Okay, over here. Okay, so I have two. So what are the ingredients of my definition? I have two non-empty sets, A and B. A function, let's call it f, from A to B is a subset of A times B. In other words, a relation from A to B with a specific property. The property is that if you take any A in big A, so your first set, it appears once and only once in a pair of this relation. Okay, so for each A in A, there exists a unique B in B such that AB is a pair in the relation F. Okay, the standard notation for functions is the one that you see here, F two dots A arrow B. What does that mean? It means F is a function from A to B. That's all that means. Okay, and as you've seen before, for other kinds, I mean, for functions of a special kind, but it's the same for all functions. If I write f of a equals to b, that's how it's read, it means the pair AB is in F. Okay, so okay, just a few. Did I? No. Okay. So here are a few more definitions associated to functions, and then we'll look at some examples. Okay. So let's say I have a function from A to B. Okay. Then what is A called? It's called the domain of F. Okay. Now you've seen the notion of domain in calculus. It was a little different. I'll get back to that in a sec. It's the same thing, but presented slightly differently. We'll see in just a sec. Okay, but formally, this is the right definition of domain. It is given with your function. Okay, B, the set on the right, is called the codomain of F. These are just names for these sets. Okay. If f of a happens to be little b, we say that b is the image of a under F. Right? Remember that if f of a equals to b, there's only one such b, right? So b is the image of a under F, okay? And the image of F, these are all the images of elements from A. So this is the set of all B and B such that f of a equals to b for some little a. So you look at all possible outputs of your function. If you think of putting elements of a in the function, right, then you look at what comes out. These constitute the image of F. Okay, so let's illustrate this. This uses words. Okay, so here in my example, I have the set A consisting of 1, 2, 3, 4. The set B consists of A, B, C, D, E. Okay, and I tell you that F is the following set of pairs: 1A, 2B, 3B, 4E. I claim this is a function. Okay, first of all, you'd have to check that it's a relation from A to B. How do you check that? The first entry of each pair should be in A. That's good. The second entry of each pair should be in big B. Yes. And finally, we must check that for each element of A, there is one and only one pair that starts with that element. Okay, so there's one for 1, there's one for 2, there's one for 3, and there's one for 4, and we're good. Okay, so this is a function. Another way to write this is f of 1 is A, f of 2 is B, f of 3 is B, f of 4 is E. Okay, that's equivalent notation. So what is the image of 1 under F? It is A. What is the image of 2? It is B. What's the image of 3? It is B also. That's legit. That's okay. What's the image of 4? It is E. So you look at all the possible values, A, B, B second time, and E, A, B, E. So this is the image of F. It is A, B, E. The domain is A, the codomain is B, the image is ABE. Okay, here is another relation. Okay, so I took this one from the book. So the first pair is Abdul 22, second pair Brenda 24, then Carla 21, Deirdre 22, Ethan 24, Felicia 22. Okay, I'm asked if this is a function. Okay, now notice I haven't been given the two sets, right? But that's a sort of side issue here, but you can still verify that R is a function provided that the set Abdul, Brenda, Carla, Deirdre, Ethan, Felicia is your first set, A, right? And that will be a function. There is exactly one pair for each one of these elements. Okay. The codomain is not specified in my example, but as long as it's a set that contains 21, 22, and 24, we're fine. Okay. But it's not specified here. What is the image? It is 21, 22, 24. Okay. But formally speaking, usually if you're given a function, you should be given the domain and codomain. That's part of the definition of a function. Which brings me to slowly to this calculus thing. And again, you don't need to know anything from calculus, but this might clear up something from calculus. In calculus, let me just skip the top example just for the moment. Let's go to the calculus example. H of x equals x squared plus 1, right? So in calculus, we're always given these functions in this form. We're just given the rule of the function. Now, if you remember, what was the domain? The domain was defined as the largest set of real numbers for which the formula makes sense. Okay, that sort of comes from engineering, but I'll take the fifth on that. But formally speaking, we should be given the domain, but loosely speaking, that's the kind of thing that we do once in a while in calculus, where so okay, the domain is just the biggest set of real numbers for which this makes sense. Okay, but I'm not gonna, obviously we're not gonna touch that. I just wanted to connect to a word, a name that you've seen before. Let's look at the first example here. With infinite sets. So it's an infinite set, but it's a discrete set. You remember, I talked about this. So we have a function g from z to z, which assigns to each integer its square. Now we could write it like that, or we can be a little more efficient and write g of x equals x squared for all x and z. Or we can see it now. So I'm trying to connect a little bit, between what we just saw, like lists of pairs, and what you saw in the past few years in calculus and high school. I'm trying to bridge the space in between them, right, in this example. So G is a function in our sense. It's a set of pairs. And for example, -2, 4 is a pair in this relation, in this function, because -2 squared is 4, -1 squared is 1, 0 squared is 0, and so on, right? So these are the pairs. As defined, the domain and codomain of this function are both z. And what's the image of this function? You have to look at the second coordinates of pairs here. What are these possible values? They're squares of integers, right? So 0, 1, 2, 4. I put a 2 here. It should be removed. There's no 2 there. 0, 1, 4. I have to fix that. Okay. Okay. All right. Hopefully this is okay up to this point. Okay. Now I want to define two fundamental properties of functions, which are injectivity and surjectivity, which are things that you have sort of seen perhaps maybe in high school, that you might revisit in linear algebra. It's important. But these are really fundamental, basic concepts concerning functions. Okay, so let's define, and they're not difficult by themselves, right? It's just you have to get used to it, playing with them. So let's start with functions which are one-to-one, or same thing, injective functions. So we say that a function f from a to b is one-to-one, or injective, means the same thing, if the following property holds. If I take a and a prime in A, and f of a happens to be equal to f of a prime, then a is equal to a prime. Now, this is often confused with the definition of function, but that's not it. Okay, function is that if you take an element in A, there is only one B in B corresponding to that, which is in a pair of the relation. But this is the other way around. Okay, it says that if you take two different element, look at the Venn diagram. I like to see it this way here. So this is what's forbidden in a one-to-one function. If a and a prime are different, f cannot map them to the same thing. You cannot have ab and a prime b in the function or in the relation if a and a prime are different. Okay, so this is forbidden. F cannot crush two inputs to the same output. Okay, so that's what one-to-one means. Okay, here are some examples. First example here, F, 1A, 2B, 3C, 4D. This is one-to-one, right? Because the values on the right are all distinct. If I look at the function G, 1A, 2B, 3B, 4E, it is not one-to-one because B here is the output for two different inputs, 2 and 3. That's no good. An example from, well, it's not calculus, but with infinite sets, function from Z to Z, f of x equals x squared. It is not one-to-one because f of 1 is equal to f of minus 1, right? 1 squared minus 1 squared are the same. So this function is not one-to-one. If you now look at a function from R to R, defined, I call it k of x is x plus 1. This is one-to-one because k of a equals k of a prime. These are your inputs. It means that a plus 1 equals a prime plus 1. These are your outputs. So obviously, a has to be the same as a prime. Okay. All right. Okay. Now, completely different concept. The notion of onto or surjective function. So I have a function from f from a to b, and I'll say that it is onto or surjective if the following holds. If you take any b in the codomain, in big B, there is an a that is mapped by f to that b. You hit everybody in big B. In other words, another way of saying this is that the image of f is the whole codomain. Okay. And again, I think this picture is a good one to think of this. So what is forbidden is something that looks like this, where you have an element of B like that, where f doesn't map anything to it. That's what's forbidden. Okay, for an onto function, that's not legit. Okay, it's not onto. Okay, so let's take a look at some examples. Notice that to know if a function is onto or not, you must know what the codomain is. If you don't know what the codomain is, there is no way to know if it's onto or not. Okay. So here's an example. G is 1u, 2v, 3v, 4y. And we're told it goes from 1, 2, 3, 4 to u, v, w, x, y. Then I say this is not onto, because if what's the image, these are the values on the right of each pair, u, v, and y. It's not equal to u, v, w, x, y, right? So x is nowhere to be seen. Okay, so I wrote f here should be a g. Sorry about that, man. here's another example. The function from z to z, f of x equals to x squared, is that onto no, you will never hit 3 as the image of an integer, right? You cannot square any integer to hit 3, to equal 3. So it is not onto. However, if you take the function k from, again, from my couple of slides ago, k goes from r to r, k of x equals x plus 1. This is onto. You can verify this if you take any real number b, right? How do you map some x to this b? Well, take b minus 1, right? B minus 1, you add 1, you get b. Okay, so this is onto. Okay, so we've got one-to-one functions, we've got onto functions, and you might ask, well, is there a connection between the two? And in a sense, no connection whatsoever. In the following sense is that all possibilities will occur. So there are functions which are one-to-one or not, and onto or not, and all the cases will occur. So I've shown you here a little picture of this. So let's look at example 1 here. The function is one-to-one. It never crushes two elements onto the same element, and it is onto. You hit everybody in the codomain. So this is both one-to-one and onto. This one, number 2, is one-to-one, so nothing is crushed, right? But there's an element in the codomain that's not hit by anybody. So this is one-to-one, but not onto. 3, this one is onto. I hit everybody on the right-hand side, but I'm crushing these two inputs to the same output here. So this one is not onto. Sorry, it's not one-to-one. So it's onto, not one-to-one. And this one is neither, right? Because it's not one-to-one. These two are crushed, and it's not onto because there's this element. I could give names to these points, right, and write out the example, or you can do that as an exercise if you feel the need to do it. So you'll have actually explicit examples of all 4 possibilities. Okay. All right. Now, functions which are both one-to-one and onto are very, very nice. They have both these properties, and they have a name. They're called bijections, also called one-to-one correspondences. Okay, but so again, a function is a bijection if it is one-to-one and onto. It has both properties. Okay. And if you look at this picture, this really shows you what you're expecting. You have 2 sets. You have your function that maps each element of the first set to the second set. It never crushes anything and it hits everything. So if you think a little bit about this, you'll see that it'll always look that way. Okay, so you're sort of, hence the name one-to-one correspondence, that you're corresponding each element in one set to exactly one element in the other set. Okay, so it's what we call a bijection. Okay, so let's try to see what this has to do with something that you've seen before in calculus, but is a completely general definition concept, the notion of composition. Okay, so it's an operation on functions which have something in common. So the codomain of one function has to be equal to the domain of the other. So this is important. Okay, so let's go through this. So I have a function f from a to b, and I have a function g from b to c. So notice that the codomain of f is equal to the domain of g. Okay, otherwise this is not defined. So the composition of f and g is a new function. It goes from a to c, and it is defined as follows. So g circle f, that's the notation for this new function. G circle f of a is g of f of a. and you've seen this before, right, in calculus, but it's a completely general concept for functions in general that like we've defined here. Okay, so here's a picture of the situation, which I think, or hopefully it helps. So I have f, which is a function from a to b, and I have g, which is a function from b to c. Okay, so I compose them. Basically, I create, if you think of f and g as little machines that have an input and an output, you plug in the output of f into the input of g, right? So that's basically the idea. So the new function will go from here to here. And how do you compute a value of g circle f? Well, you take this little a, you compute f, and then you compute g. Okay, so that's the new function. Okay, so here's an example. So I've given names to the elements in my diagram. A is 1, 2, 3, B is U, V, W, and C is RS. F, as you can see, is the function 1U, 2U, 3V. I just wrote down exactly what's here. And G is UR, VS, WS. Then G circle F turns out to be 1R, 2R, 3S. Okay. All right. So that's an explicit example of a composition of functions. Okay. So what's the connection between composition and bijections? And it's a fundamental one. Okay. So it turns out that a function is a bijection precisely if there is a function that cancels it when you compose. So how do you cancel out functions? This is how it goes. Okay. So I'm saying here that f is a bijection precisely if it has an inverse. So what is an inverse? It's a function that goes back from b to a, right? F goes from a to b, g goes from b back to a, such a way that if you compose them, nothing happens. So f circle g of b brings you back to b. And if you do it the other way around, if you go g circle f of a, you get back a. So you start in one set, you take one of the functions, you go to the other set, and then you come back via the other function, nothing has happened. And this should be both ways. Okay, so that's what we call an inverse for the function f. Okay, now I'm saying that a function is a bijection precisely if it has an inverse. Well, let's think again of this little picture we had for a bijection, right? So it's injective, never crushes anything, and it's onto, you hit everything. So what could possibly be the inverse? You can probably guess what it is. You just flip everything. You see I was really lazy. So that's what the inverse is. Okay, so if you have a bijection, if you flip the pairs, you will get and you see that, I mean, that's the intuition behind in one-to-oneness and onto-ness, right? Let's go back to original function. If I flip those pairs, I want to make sure I have a function. Okay, so to make sure I have a function, I can't have this function be not one-to-one, because then I'd have two A's going to one B. If I flip those pairs, the flip will not be a function. I'll have something going out of one value going to two values. That's bad. And the second thing, I must make sure that I have an arrow or a pair that starts with every possible value here. That's why I need f to be one-to-one. Okay, so one-to-one, onto, these are basically the requirements for to make sure that when you flip those pairs, you still get back a function, and that's the inverse of your function. So that's the connection between these two things. Okay, to end today's lecture, I'm just going to talk about very briefly some special functions that you may have seen or not in calculus. It doesn't matter. They're simple functions, or sort of simple, useful anyway. The floor function. So the floor function, this is the notation. So it is defined, its inputs are real numbers, okay? And what is the floor of x? This is the notation, right? You think of floor. This is the largest integer less or equal to x, okay? So basically what you do is if you take a real number, you throw out the fractional part. You throw out the decimals. That's your floor function, okay? What is the ceiling function? Almost the same thing, except rather than throwing out that part, you go up. So this is the smallest integer greater or equal to x. So you just go up to the next integer. So 3.7 goes up to 4. Okay, and I've given you examples here. So the floor of 1/2 is 0. The ceiling of 1/2 is 1, as expected. Okay. Same for negatives. Floor of pi is 3 point something. So floor is 3 and ceiling is 4. E, floor of E is 2, ceiling of E is 3. If you have an integer as your input, then obviously nothing happens. Floor and ceiling of 5 or 5. Okay. So this is a way of taking real numbers and making them into integers, right? You take the closest integer to your real number, either on the left or on the right. Okay. Yeah. In computer science, the most convenient log is log base 2. So it's the logarithm of x base 2. So in the book, you'll see that when you see log x, it means log base 2. We won't be using it very much, but if you see it, you should know. One little trick to remember what log x means, it is essentially the number of bits required to write your number in binary. Okay, -1. So this gives you at least a size of the thing, and it's a useful thing to keep in mind. So log 16 is 4. Why is that? Because 2 power 4 is 16. So that's the definition of log base 2, right? The exponent you give 2 to get the number you're interested. And 16 happens to be 10000 in binary. So that's 5 bits. -1 is 4. That's exactly what you want. And one last function that you very probably saw in Cal 2 is the factorial function, right? Which is n. No. N factorial is 1 times 2 times 3 right up to n. That's if n is at least 2. N is an positive integer. 0 factorial and 1 factorial are equal to 1 by convention. There's a reason for that, but later. And that's it for today. And so I'll see you next time. Cheers.